Hello and welcome again to my physics online video lecture series. In today's video we're going to be talking about the Heisenberg Uncertainty Principle. This is a continuation of our discussion, introduction to really, survey of quantum mechanics. The Heisenberg Uncertainty Principle follows from some of the previous principles such as the de Broglie theory, his hypothesis that particles, or what we once thought of as being particles only, have also a wave-like nature to them. We talked a little bit in our previous videos. I discussed classical uncertainty a little bit. And classical uncertainty it's fine. It gives you a model to start thinking about Heisenberg's uncertainty, but there's more to it than just that in some sense. The uncertainty principle is kind of a fundamental principle in quantum mechanics, and there's some philosophical discussion about it, quite a bit actually, that I don't necessarily want to get into too much in today's video because it's too short. How do we interpret the results of quantum mechanics? Is uncertainty a baked-in fact of nature? Is it just a limit on how much we can know about nature? These are kind of philosophical questions that I'm not going to discuss so much in this video. Heisenberg and Bohr and some others basically came up with what is sometimes called the Copenhagen interpretation for quantum mechanics. A lot of these guys were Dutch, and essentially this interpretation can be boiled down to a process that can't be measured exactly doesn't happen exactly. So that's one interpretation of quantum mechanics. Others would argue that this is not reality per se, that maybe the process does happen exactly, we just don't have any way to actually measure it. And I don't really want to go down that particular rabbit hole too far. I mostly just want to present what the Heisenberg uncertainty relations say. What are the rules basically? And we find that these uncertainty rules do pop up beyond just the two that I'm going to present. But I'll start with these two things. Maybe we should begin by recalling, if you've watched it, my other video when I talk about classical uncertainty. Essentially, there are some limits to what we can measure, or the precision to which we can measure things. And these limits are in part due to the tools that we have available, but not entirely. So for example, in Physics 1, I usually introduce the idea of standard deviations and of repeated measurements. Sometimes in class when I'm teaching Physics 1, if I have the time on that day, I will actually have students walk up to the board, the blackboard at the front of the room, and measure how long it is from one end of the board to the other. And those measurements, as long as they don't communicate the measurements to each other and bias it, there's usually a distribution of measurements that people make. And this is true even if I've handed everybody a meter stick and said use this. It's still true, by the way, if I hand them a tape measure, as long as I tell them that they can't run it along the top or the bottom of the board. They have to pick somewhere towards the middle of the board or some such thing. And there will inevitably be some distribution of values for how wide the board is, even if the board does have a specific width. And, does it have a specific width? Well, okay, on a small scale, let's say the thing was machined or milled, there's usually a plus or minus some fraction of an inch or some fraction of a centimeter or some fraction of a millimeter precision to it. But oftentimes the imprecision from these measurements will be on the order of a few centimeters, which is much larger than whatever imprecision came from machining it. Okay, so that's sort of measurement uncertainty, measurement precision stuff. And you could improve the experiment and maybe get better measurements and so on, but there ends up being some limit, even classically. But that limit usually is more a matter of what are we technically capable of doing. Now, philosophers such as Stanley Yaki have argued that classical scale objects such as a cloud, for example, might be a little bit difficult to measure. How wide is a cloud? What do you define as the edge of a cloud? And even on bigger scales, how big is our galaxy, for example, or how big is our solar system? And that varies based on what kind of definition you want to use for either of those things. But even for something as simple as like this calculator, like how wide is it from one end to the other, is going to vary a little bit. On quantum scale, though, even when everybody is in agreement with the definitions, even when you have something that should be relatively simple to measure, there is some built-in uncertainty to it. And the standard approach for this is given by, for example, Giancolli in his textbook. Actually, Sears and Zemansky also go into this. They use a slightly different approach. They talk about the double slit and how one way to interpret the results of the double slit with even particles like electrons or alpha particles or what have you, is to say, well, the narrower that we make the slit that we're sending them through, and this is true for a double slit, this is true for a single slit, the narrower we make the single slit, let's say, the better we know where the exact position of the particle is that has to pass through that slit. So we know the position in this direction very well. Okay, so compare this slit, let's say, versus this slit. Okay, this one right here, if this is my y direction, my delta y is precise. This one right here, if this is my y direction, my delta y is not precise, comparatively speaking. So we might say relatively over here. Relatively. And the smaller you make this slit, in some sense, the more precisely you know the position of the particle that is traveling through the slit. Particle could be here, here, here. Particle has to be more or less here. But then you look at the pattern that comes out on the screen. So if I move this part of it over a little bit, this one right here that has a very non-precise sort of slit value, if I look on the screen removed, I end up getting some diffraction pattern that's maybe relatively narrow, relatively high in the middle, and then second, third, etc. This one right here, I end up getting a more broad pattern on the screen. So my diffraction stripes are sort of broader. And the only way that you can account for that in terms of particles is to say that these particles more or less have momentum in this direction. In other words, they don't have much uncertainty in the y component, delta py is relatively small. And over here, this particle, in order to make this pattern, could be moving off like this, could be moving off like this, could be moving off like this. In other words, delta py is relatively large. Alright, so smaller uncertainty in the position here means larger uncertainty in the position out here, and vice versa. Now, you can go through and do a calculation and figure out what should the relationship between these things be. What you end up getting is, if this right here is my slit width, let's call this delta y is approximately slit width A, and then down here same thing, then delta y times delta py is approximately, as it turns out, Planck's constant h. Now, Giancali's approach to getting this same result is very similar. Let's say that I happen to have an electron. Let's say that I want to measure the position of the electron. How do I do that? Well, I have to send something like a photon in to measure it. And so when I see that photon scatter, I can see where it scattered from, and that gets me the position of the electron. But how much photon scatter is there going to be from this electron? Well, essentially, we know from our discussion of Compton scattering, or if you've watched that video, you know from Compton scattering, that this photon may shift in its wavelength when it scatters off of this electron. And so I end up getting some amount of momentum deposited on this electron that wasn't there before. And we know that the momentum P is equal to h over lambda. And so in some sense, the delta P that could be deposited is given by up to h over lambda. But my delta x over here is of order wavelength lambda. You know that from diffraction theory. And so once again, we can say something like delta P delta x is approximately equal to h. This works also with energy. For energy considerations, I know that I can deposit up to the energy of the photon, which is hc over lambda, and so delta E is approximately hc over lambda. Similarly, if we want to figure out the uncertainty in time, using similar arguments as we did here with diffraction, the uncertainty in time should be of order the period, which is lambda over c. So these are going to be reasonably close to each other. And so if I multiply my delta E by my delta t, then I have hc over lambda times lambda over c. And I can cancel some terms here, and I get approximately h. Now, these are very simple calculations in some sense. Basically, the argument is not very rigorous here. We've kind of made some approximations. What Heisenberg did was he kind of made these calculations more precisely. So after more rigorous, more precise calculations, what Heisenberg obtained was that delta of x or y or what have you times delta p of x or y or what have you must be greater than or equal to a quantity called h bar, the Planck reduced constant. By definition, that's just Planck's constant divided by 2 pi. Similarly, for energy, delta E delta T must be greater than or equal to h bar. So the Planck's constant h is about 6.26 times 10 to the negative 34 joule seconds, or 4.136 times 10 to the negative 15 eV seconds. Therefore, Planck's reduced constant is about 1.055 times 10 to the minus 34 joule seconds, or 6.583 times 10 to the negative 16 eV seconds. All right, so these are your minimum uncertainties. Now, a system may exist in which the uncertainty is greater than this, but a system should not exist in which the uncertainty is less than this. And as we study quantum mechanics, as we learn about Schrödinger time evolution, about superposition states, about how uncertainties are calculated, that kind of thing, we discover that this holds out pretty well. Maybe a couple more words on the uncertainty. These uncertainties, delta x, delta p, delta e, delta t, all these things basically represent more or less a standard deviation for the measurement of the quantities that they are being used to measure. All right, so this is not to say that we're equally likely, if we've said that the position is at, let's say, 1 centimeter, sort of exactly as our average position, and the uncertainty, let's say that we represent, maybe we go down onto picoscale. So we say this thing is located at the position that we're defining as 0, and the uncertainty is 2 picometers. That does not mean that we're equally likely to find the object 2 picometers away from 0 as we are at 0. It is a standard deviation. Statistics apply. At the standard deviation point, your probability density has fallen off by quite a bit. You have approximately a 66% chance, or 68% chance, of finding the particle between 2 picometers to the left and 2 picometers to the right, if your measurement is left-right. You have approximately a 95% chance, 94 point some percent chance, of finding it between plus or minus 4 picometers. You still have a pretty good chance, almost 50%, of finding it between plus or minus 1 picometer. So we're not claiming here that you're equally likely to find the particle at 0 as at 2. In fact, we're not claiming that you're likely to find it exactly at either of those positions. It may be, it may not be. This is going back to this uncertainty idea. The particle, we can't necessarily measure the exact position. We start going into what are called probability density distributions. Second note, there are other things beyond position, energy, time, and momentum for which uncertainty principles can be applied. For example, many particles have what is called spin. This is intrinsic angular momentum, not orbital angular momentum, but intrinsic angular momentum. And as it turns out, spin is a quantity that has a sort of uncertainty relation. So you can measure spin, intrinsic angular momentum, along any of x, y, z axis. So you can have a delta x, we could call this delta spin x, delta spin y, and delta spin z. And as it turns out, when you measure along one of these axes, you lose information about the spin along the other two. So perhaps I measure along the z-axis. If I measure it to be spin up, for example, then I know what the spin is. And in fact, I now know with actual certainty that all of the particles are spin up along z. But they also end up going into a superposition state for x and y, so that I don't know whether the next particle will be up or down. In fact, it's a roughly 50-50 chance. Now, as it turns out, the possible measurements for an electron are either half of the reduced Planck's constant positive or half of the reduced Planck's constant negative. Basically, this has to do with placing the electron in a magnetic field and then watching its deflection. And of course, we're kind of papering over any discussion of delta x being whatever it is. You know, we're neglecting discussion of uncertainty in delta x and in delta p for this. So these are your possible values, and this is true for x, for y, and for z. Now, if I send the particles through z, and I measure them all to be plus h bar over 2 for spin, then any of those particles has about a 50-50 of being plus or being minus h bar over 2 when sent through the y detector or sent through a z detector. The end result of this is that we can say something like delta sz is 0, and delta sx and delta sy are both h bar over 2. Okay, so both of those have h bar over 2's. So possible result. But this means that my total uncertainty, delta sz plus delta sx plus delta sy, is equal to h bar. And again, it's kind of correct to say these are all inequalities. So this actually is greater than or equal to h bar. Means that even in something that is not delta x or delta y or delta z or delta p or delta e or delta t, these uncertainty relations crop back up if you know how to look for them. Now, this one's interesting because it's experimentally verified. These you can get from what are called Stern-Gerlach experiments. And you can set up the Stern-Gerlach experiment to measure first, let's say, z, and then take only the positive outputs from z. Then measure x, or then measure y. And you end up getting these uncertainties every time in these experiments. And this is an entirely separate kind of calculation than was done over here to estimate what are my uncertainties for position, for momentum, for energy, and for time. These ones we're not measuring those things per se, although those uncertainties can be kind of in the background in the form of delta x and delta p and so on, which means that you would expect a slightly larger value if you're trying to do a measurement of the value of the spins, as opposed to just simply knowing this result from having obtained it in previous experiments. So this uncertainty principle is fairly widely applicable within quantum mechanics. And that's all for today's video. Thanks for watching. Hope you found it interesting. And see you in the next one, I guess.